Okay, so it's my great pleasure to introduce Philip Saville, who's of course known to lots of people here, maybe even everybody here. Philip has just finished doing a PhD in our group here in Cambridge, here in the loosest sense of the word, under the supervision of Marcelo, and he's now working with Ohad Kamar at the University of Edinburgh, and he's going to tell us about some of the work that they're doing together on full abstraction. Over to you, Philip.
Well, yeah, thank you for having me. So this is joint work with Ohad and Shinya, and it's about full abstraction in the style of a paper by Ohad and Riki, which is, I think, unfortunately not as well known as it should be. So it's a little bit overshadowed by all the work on full abstraction in the game semantics world, which is obviously set off this huge new field. And then the Ohad and Riki paper is, I think, a little bit later or about simultaneous, and it constructs a fully abstract model for PCF, but it's somehow a little bit overshadowed. But what we're going to do here is we're going to do a categorical reconstruction of that model for Moji's monadic meta language in a particular case. So we'll see how things go. And the first thing I want to say is a kind of apology and/or warning, because Jamie asked me to talk about this work about a month and a half ago, and I thought, yeah, great, I can talk about this because it will be beautifully clean and polished by now. Obviously, life being what it is, it's not quite as polished as I had hoped, but I'm hoping that all the sort of key components will be clear enough. It has a lot of moving parts in this construction, so and you're the first like trial group of people I'm presenting it to, so. I'm hoping it'll come across, but I'm sorry if it gets confusing. So stop me.
In my experience, talks about work in progress are usually far better than talks about work that's finished, because work that's finished, people try and make it seem totally polished, and it's completely incomprehensible and so fancy. But work in progress, it's easier for you to somehow expose what's really going on. And I wouldn't apologize for that at all.
Well, so hopefully this will be it won't be needed, but just as a warning, this is still things to do and things still to be polished in various places. So let's start by thinking about full abstraction. So what is full abstraction? It's a property where you've got some language, and it means that your operational semantics coincides with your denotational semantics. So we can put that a little bit more precisely. We have this notion of contextual equivalence. So this is contextual equivalence for PCF. Where you say two terms are contextually equivalent if essentially they behave the same in any context. So I can take the program out and put the other one in, and my overall program won't change. So what that means is that anywhere that I can put M in a context and reduce it to some term V, then I can put M prime in the same context and it'll have the same behavior. And then the sort of terminology, I've always found it quite difficult to remember all the different sort of terms. Adequacy is the property that if I want to check contextual equivalence, I can just check whether the denotational equivalence holds. So I can just check whether these are semantically the same thing. But what I can't do with this is refute contextual equivalence. I can't say, well, these two are not equal, therefore they're not contextually equivalent. To do that, I need full abstraction, which is the converse. And in general, if you sort of speaking
Philip.
Yeah, go on.
Can I say something? Full abstraction, you mean if and only if there. Full abstraction is both implications.
It depends on your sources. I sometimes use it as full abstraction as an if and only if, but I think I went back to some of the earlier papers and they take it as an if. I'm not sure on that. I think that's the way it goes.
But I'm assuming you're at least self-consistent within your own talk, and at the top you coincides with. So doesn't that that you should have a left-right arrow instead of just a right arrow there?
Yeah, that is true. That is true. The reason that I'm thinking of coincide with here is I'm thinking adequacy is generally something that's quite easy to prove. I mean, easy for a given level of easy, but it's usually you can do some kind of logical relations argument. So that's not so difficult.
I see. So you mean this is the difficult bit? So
the difficult bit is always is proving full abstraction. And between Plotkin's paper and the Hylandong and the Abramsky-Jagodizin papers, it took 15, 20 years for the full abstraction problem for PCF to be solved. And the kind of fundamental problem is that your model is usually too rich. So what that means is, particularly at higher types, right? So I've got two functions and they might agree on all the definable bits in the model, but if there's something that's not definable in the model, I can pass that in and the functions might now disagree. So this happens in PCF because I have this parallel or thing, which isn't definable. And then I have these two terms which are contextually equivalent. They agree everywhere, every time I pass them something definable, but then I can pass them this thing which the language doesn't know anything about, and that distinguishes these two otherwise indistinguishable functions in the model. So like I said, this full abstraction problem for PCF, the game semantics was one of the a big leap forward, which took a completely new perspective on this, away from the domains model, and come up with fully abstract models. But there's also this O'Hearn-Riki paper, which starts from the domains model and does some kind of logical relations style argument to build something fully abstract. And that's what we're going to be working on today. This is the kind of starting point for the work here. And what we're going to be, I think I said in the title, in the abstract, I was going to do it for something like the computational lambda calculus, but there's some complexities involved if you do it with that that go away if I use the monadic meta-language instead. So I'm going to use the monadic meta-language just because it makes some of the theory a little bit simpler. So a quick review of the monadic meta-language. We take the simply type lambda calculus and we extend it so that for every type sigma, I now have this monadic type, this effectful type T of sigma. And I have two new term formers, one of which takes a term and turns it in, takes a pure term and turns it into something effectful. So it's marking it as possibly having the effect. And then the second construct is a means of chaining together effectful computations. And actually, what we're not going to focus on the language very much, so we're not going to need its details. All we're going to need to know is that a model for this language consists of a CCC, a Cartesian closed category, which we use to model the simply type lambda calculus part, and a strong monad, which we use to model these extra bits. So T, the interpretation of T sigma is T applied to the interpretation of sigma, and we use the strength for this chaining together of effectful computations. And the final thing we need is an interpretation of base types. We just have to pick something for the base types to be in our category. And then in the standard way, like you do for almost any language, this interpretation and this structure determines an interpretation of the whole language, which you're going to write S semantic brackets all the way through the talk. Okay, so this is what the models look like. And I don't really want to work with, because later on in sort of future work and some of the work we're doing, we're extending this language in various ways, adding in some types, adding in different kinds of operations. And so we don't really want to be having to worry about the operational semantics all the time. So we're going to phrase contextual equivalence semantically. This gives us a way to work completely semantically without having to worry about these various syntactic complexities. So we're going to say that two terms are contextually equivalent if and only if their semantic interpretation coincides whenever you put them in a closed ground context. And it's a sort of small lemma to prove that for PCF, this coincides with the usual syntactic notion. So this isn't a completely crazy thing to be doing. And it now lets us define full abstraction as this property that contextual equivalence defined in this way implies semantic interpretations are equal. And this is the thing that we're going to be trying to prove in this.
Sorry, Philip, if this is a stupid question, but what is, syntactically, what is contextual equivalence? I mean, the other definition of contextual equivalence.
Contextual equivalence is usually you have some operational thing that their operational semantics is the same in every closed ground context.
So is this like definitional equality, or is that not what you mean?
No, it's intersubstitutionality. It's that if in the sense that in any enclosing context they behave the same.
Okay.
So it's weaker. I can never remember which one is weaker or stricter, but it's not the same as definitional equality. Definitional equality identifies few things, but this will identify more. It identifies programs with the same kind of behavior.
Right. So it's a weaker notion in that sense. Yeah. Okay.
Yeah.
Sorry, I just have another question.
Yeah.
So in your second box, you say contextual equivalence means that for any closed ground context, S of C of M equals S of C of M prime. Mm-hmm. And then for your implication for full abstraction, why can't you just pick the the empty context, like the do nothing context?
Because it might not be a ground type and it might be an open term.
Oh, okay.
Does that make sense?
Yep.
Just check, because I might have also said something stupid, so it's good to be sure that.
No. The ground bit is the bit I didn't.
You haven't said anything stupid yet, Philip.
Okay, good. We've got 5 minutes in.
Andy will immediately tell you when you say something.
I'll try.
Okay. All right. So this is our notion of contextual equivalence and full abstraction, and we can simplify this a bit, the problem a bit, by saying that full completeness and extensionality implies full abstraction. I'm going to tell you what these things are. So there's a standard argument for PCF that if it's in Streicher's book, for example, that if you have a model for PCF in which, in the domains setting in which everything is definable, then that model will be fully abstract. And the reason is because, well, I'm going to show you what the reason is in a second, rather than trying to tell you now. So a model is extensional if global elements distinguish morphisms. So what I mean by this is that F and G are equal if and only if every global element from one into the domain, they agree, the composites agree. So in set, for example, this just says that F and G are equal if and only if F and G agree on every element of A.
Did you not like the existing word well pointed?
Well, I think I saw well pointed is sometimes used for categories, but I think I saw in some of the denotational semantics literature they use extensional to refer to a model instead. So I was, yes, well, it's equal to B. It's exactly the same as C being well pointed. Yeah, that might be a better term to choose. And here's some more terminology, which is not, I'm not particularly a fan of, that it's called fully complete. A model is fully complete if every morphism is definable. So we can now show that if it's extensional and fully complete, then it's fully abstract. And I'm just going to give you an outline of how this argument works. In a slightly simpler case where I've only got one variable in the context, because that makes life a bit easier. But once you see how it works, you can then extract the general argument. So I've got these two terms that are contextually equivalent. And then to show that they're equal, that their interpretations are equal, then I have to show by extensionality that they agree on every closed ground term, they agree when composed with every global element. But then the global element must itself be definable by full completeness. And then that means that then by sort of standard compositionality properties, I can build a context in which I just feed in this term here for X. By contextual equivalence, they must agree, and so I get the equality that I need. So really the problem for full abstraction is really a problem of full completeness. And a lot of the work you'll see in building fully abstract models is trying to build fully complete models. Okay, so then this is our sort of problem that we want to deal with. We want to say,
can I just make a quick comment?
Yeah, go on.
Yeah, so one should bear in mind that you're sort of making life simpler by not having, recursive constructs around. So
yeah,
so everything is finite if you want to put it that way. So I mean, if you were doing PCF, not everything, you wouldn't want full completeness for all things. You'd want things to be limits of
yeah,
finite things, right? So
yeah, the word compact usually appears at some point, doesn't it? When you do this. So yeah, yes, when you're doing it in domains, we do it order enriched. You need some kind of limit, like, yes, it's a little bit more subtle when you order enrich. But yes, so what we're thinking is we haven't got around to enrichment yet, so it's all nice and set based, which means it's a little bit simpler. And this is also quite a strong assumption because it won't hold, for example, in general in a pre-sheaf model. So we have some kind of, one of the bits that's in progress is a little bit more refinement to get away from this assumption. But still, the kind of fundamental thing you want to build is a fully complete model in our setting. Okay, so our starting data is some model, a category, a monad, and interpretation. And what we have is we have these two goals that we've got to make. So this is going to be our target. We want to make every morphism definable. So we want to map in the category, but we also want to somehow internalize this criterion so that if if I've got f and g in the function space, then they're only going to be distinguishable if I can distinguish them on definable elements. So what I don't want is something that happens in for example, PCF, where I've got elements of the function space which I can tell apart by feeding them arguments. So I want to make sure that this doesn't happen. So somehow criterion 2 somehow internalizes criterion 1. And we're going to need two kind of different things to handle this. And both of them are in the O'Hearn-Ricci paper in one way or another. So the first thing we want to do is we want to characterize what it means to be definable. And we're going to use some kind of logical relations argument for this. And we'll ensure that every map preserves these kind of relations. And that will be enough to make sure that every map is definable. And the second thing we need to do is we introduce what we're going to call concreteness, which is going to cut down our function space so that it essentially throws away the bits that are bits that we don't want. Concrete is a term used by O'Hearn-Ricci as well, by the way. So if you look at their original paper, you can see how it fits in with what they're doing. I'm going to take this stage by stage, and this is why there's a lot of moving parts in this, because we need to kind of tick off each of these three different things. So we're going to start with this characterization of definability. So let's sort of think about what you might call the definability problem. So you can talk about this for any language and any class of models, really, but here we're talking about it for the monadic meta-language. So we want to characterize the maps which are definable in the monadic meta-language in some model. And usually the way you do this, and I'll just review it in a moment for the simple type lambda calculus, is we define a category of relations over the objects in C, a category of cryptic relations. We observe that this category is itself a model, so a CCC, for example, and then we can say that the definable maps are those which preserve every relation of the appropriate form. So let's see how this works. So the category of cryptic relations of varying arity. So this goes back to Jung and Turin, and it was put in categorical form, I think, by Ali Mohammed in quite a nice paper. And so starting data is a Cartesian closed category and a Cartesian functor from a category of contexts and renamings into our category. And you can think of this as somehow a generalized notion of semantic interpretation, because this functor will be determined by its action on all the types, and then it just extends by the Cartesian structure to all the contexts. So at some point, we're going to think of F as the semantic interpretation, but at other points, we're going to want to have something a bit more general. And then the objects of this category are pairs. So we have some object in C and some cryptic relation, some predicate over the object. So what this consists of is families of maps, such that for every context gamma, we have some family of maps which go from f of gamma to w, and it's going to be compatible with the renaming of variables. So the example that you should have in mind with this is that if you take C to be set and the size of f of gamma is n, then this is just picking an n-ary relation over w. So these are somehow a categorical treatment of what it means to be a relation over an object. And the maps, like I said, we want maps that preserve the relations. So a morphism in this category is a morphism in our underlying category C, which preserves the predicate. So if I've got something in the predicate at R, then applying F to it, I'm still in the predicate at R prime. So this is the category of cryptic relations. And there's a kind of standard fact that this category is a CCC, and we're going to write this sort of horseshoe for the exponential. And notice here that the carrier of the exponential is the exponential of the carrier, by which I mean that if I do, and this is true for the Cartesian closed structure actually, that if I do a product or an exponential in this category, then I just take the product in the exponential in the base category, and then I just have to think about what this relation is here. And if what this exponential does in sort of a concrete case over set, for example, is sort of intuitively, if I've got f1 to fn in this exponential, that means that as in any future world, so in any sort of renaming, and I've got x1 to xm in there, then if I rename or reorder my f's according to my renaming and apply them to the x's, then I end up in s of delta. So if you strip out all the renaming stuff, the varying arity bit, this just says that if x1 to xn are in here, then f1 of x1 to fn of xn is in here. So it's really a kind of preservation condition plus some cryptiness. And I'm also I'm not going to rely on this a huge amount, but it's something that I want to point out is that this category can be constructed abstractly as you take the sub-object vibration here and take this change of base along the nerve to get this new vibration. This isn't a picture you necessarily have to understand in detail, but you have to recognize it later on because I'm going to make some tweaks to it. And then we're going to use those tweaks as we build the O'Hearn-Mieke model. Okay, so when it comes to definability, the particular case we're interested in is indeed the case where the functor is the semantic interpretation. The object W then can be the interpretation of sigma, and the relation could be the definability predicate. So it consists of all the maps in this HOM set which are definable. So they are the denotation of some term in the language. And so this gives us kind of a first step to characterizing definability, because then for every type sigma, we know that we have this object S of sigma, definability of sigma is in the category of cryptic relations. This is quite nice. It tells us that we've got the right objects in the right kind of places, but it doesn't tell us much about how we can check if something is definable. It doesn't give us a kind of criterion for definability. So we want to characterize the maps in our base category that are the definable ones. So how are we going to do that? Well, what we're going to do, we go back to this picture that we had before, and we're going to pick an interpretation. So remember, this is a Cartesian closed category, and this functor down here strictly preserves the Cartesian closed structure. We're going to pick an interpretation upstairs, so we're going to turn this into a model. So we're going to say at a base type beta, we take the carrier to be the interpretation of beta downstairs, and we take the relation to be the definability relation at the type beta. And then by a kind of inductive argument, you can show that the interpretation upstairs at type sigma is actually the interpretation downstairs of type sigma and a definability relation at sigma for every lambda calculus type, simply type lambda calculus type sigma. And the first time I saw this, I thought this was completely trivial, but actually there's some proof involved, because you have to show things like this exponential upstairs between definability at sigma and definability at tau is equal to the definability at sigma arrow tau. And if you unfold what you're having to do here, it's exactly a kind of logical relations of varying arity argument that's in the Jung and Turing paper. So what this tells us, now we can deduce that a map in downstairs is definable if and only if it lifts to a map upstairs. And indeed, you can now give I'm not going to go there because I don't want to talk about it too much, but you can give a notion of logical relation here. And then that you can say that F is definable if and only if it preserves every logical relation. That's kind of an aside. This will be good enough for us. So in one direction, so we have F is a map from the interpretation of gamma upstairs to the interpretation of sigma upstairs, if and only if it's a map by this property between these two objects. But then that means it preserves everything in here to takes something from everything in here to everything to something in here. The identity is always definable. So that means that F of the identity is definable. So that means F itself is definable. And going the other way, if I've got a map that's definable, then because of the standard compositionality properties, it's certainly going to preserve the definability relation. So that's how you get this if and only if. So the kind of takeaway from this bit that we've just seen is that the definable maps in C are exactly those that lift to the Cartesian closed category of cryptic relations with this interpretation. Okay. Now there's a little bit still to do because we're working with a monadic meta-language rather than simply type lambda calculus. You know, monadic meta-language has some extra stuff in it. So the question is, what do we do with monadic types? And so what we're going to need is a little diversion into monad liftings, and in particular lifting monads up vibrations. If you don't know anything about vibrations, don't worry. It's not crucial, but they are going to turn up in the next couple of minutes. So just ignore them for the next couple of minutes, and then you can come back once they're done. So what we have is this notion of a lifting of a monad. So I've got some functor coming down like this, and I've got a strong monad downstairs, and a lifting of this monad down, T is just a monad up here, such that all the structure, the strength, the unit, the unit, and the multiplication all lie above the structure of this monad that I started with. And then the question becomes, well, how do I construct a lifting? Do I have a sort of standard way of lifting a monad from downstairs to upstairs? And there's a slight generalization of some work by Shinya, is top-top lifting, which was itself a semantic treatment of some of Andy's work, which starts with a monad downstairs, or two monads downstairs, which are related by a monad morphism, and a lifting of the second monad T. Okay, and then it turns out that if you apply the vibration, the Cartesian property of the vibration, then this definition here, so the Cartesian lifting of the monad morphism, defines a new monad S hat, which becomes a lifting of this monad S. The important case for us is where we can take the target monad to be the continuation monad, because the continuation monad, this is Cartesian closed, so we can take the continuation monad upstairs. This is Cartesian closed, we can take the continuation monad downstairs. This completely preserves the Cartesian closed structure, so this one lies over this one. And by abstract nonsense, there's a canonical monad morphism from T to this continuation monad. So this gives us a way to lift a monad T just by picking an appropriate lifting parameter, or indeed set of lifting parameters in our upstairs category. And if you look at what this does, if you strip out all the variarity stuff and just look at it in the binary case, T is in the upstairs relation applied to the lifted monad applied to some relation S, if and only if whenever I look at some something in the relation from S to R being our choice of parameter here, then I can chain them together and get something that's in R. So if you're familiar with top-top lifting, this is Shinya's semantic treatment of top-top lifting. Okay, so the important point here is that if I pick a lifting parameter, I can lift the monad. And so if we come back to our picture here, so now the vibrations have gone, we can just think about this picture again. And now I've got this monad downstairs, and I know that by applying top-top lifting, I can make a monad upstairs, and this projection functor is now going to strictly preserve the Cartesian closed structure and the monad. And there's a kind of small lemma here to prove, but if you pick the right lifting parameters, you can set things up so that the upstairs monad applied to the interpretation of sigma upstairs gives you exactly the interpretation of T of sigma upstairs, from which it follows that the interpretation of sigma is upstairs, exactly the interpretation of sigma downstairs, and the definability relation for every sigma, including the monadic types. So then, just as we had before, we get that a morphism downstairs is definable if and only if it lifts to a morphism upstairs. And so sort of the summary of all this that we've seen so far is that the definable maps in C are those that lift to definable maps up here with this model structure. So it's this category, this chosen monad here for the right choice of top-top lifting, and this interpretation S hat. Okay, so this gives us a criterion for telling which maps are definable. This gives us kind of a way of talking about definability. So this is kind of the first part of this bit ticked off, and I'm going to leave the second part for later, and instead going to think about this concreteness condition. So, and for simplicity here, I can do it slightly more generally, but there's a little bit of the kind of work in progress element here coming in. We're going to, instead of picking an arbitrary model, we're going to simplify things a bit by picking a set-based model. And in particular, we need to pick a small subcategory of set. This can be a very large subcategory in kind of set theoretic size, but in terms of the kind of classic small, large distinction of categories, we want something small for technical reasons later on. Okay, so this is what we're going to be working with. And we want to sort of characterize what it means for it to be concrete. So what does this mean? Well, let's go back to this idea of cryptic relations. So a cryptic relation over set K, set kappa, now consists of a set and a predicate over that set. Sort of pulling out O'Hearn-Riki's definition, we're going to call an element of W concrete if the constant, so the diagonal x is in R gamma for every context gamma. And we're going to call the whole object concrete if every element is concrete, which means that the diagonal relation at W is in every R gamma for every context gamma. It's a little bit mystical, I think, and I don't have a really good sense of why this works, but my intuition is that if you unwrap what's happening, like we did for the definition of the exponential in the category of cryptic relations, what this says is that a function is concrete if when I look at some x1 to xn in this relation, then f of x1 to f of xn is in the target relation. So the way I think of this is it's saying, well, I can detect whether two morphisms are equal, two functions are equal, by only looking within our R and S relations. And if you're familiar with sequentiality, like the Sieber paper, for example, I mean, I think it's doing something similar to sequentiality. That's my intuition for what's going on here. But the kind of crucial thing is that it cuts down the function space in the right way. And so what we're going to be doing is we're going to throw away all the objects that aren't concrete. So we're going to restrict to a full subcategory of just the concrete objects. And what we're going to want to do is want to be able to build a model structure on this concrete category. So we want to be able to interpret our language in this concrete category. So the way
I want to ask a question here. Could you go back to your previous slide?
Yeah.
So the kind of my question is, at base types, what do you do? Because like you have your choice of R, right?
Mm-hmm.
So what are you going to choose at the base types, or are we going to see that?
That's part of the, there's a little bit of a trick to do it. So we have to make some kind of concreteness assumptions on our base types later on. I think that's not too strong an assumption, but I haven't been able to check yet. But there is some kind of tricky things you have to do around base types, which O'Hearn and Ricci don't have to do because they don't have base types in their language. But it turns up later.
Okay, I'll wait then.
If it doesn't make sense later, then yeah, feel free to ask again.
Is it not the case that for base types, everything is concrete? I was expecting that would happen.
We're going to make an assumption along those lines, yes. Okay. We're going to need that, yeah. Yes, and it's not, I think that's not too strong an assumption to make in most situations. Although that one of the things we still need to do is sit down and work out some examples in detail just to check exactly how strong these things are. But yes, base types is something that is an added complexity, which is something new that we're having to work with over the PCF-based setup. Yes, so what we want to do now is turn this subcategory of concrete objects into a model. And it turns out you can do it by kind of abstract nonsense. So we're going to start off with our set K. It has some model. We've got some interpretation of base types. We've got some monad. We're going to assume we've got any lifting at all here. It doesn't have to be a top-top lifting. It could be any one at all. And then we're going to take this subcategory. And it turns out that this subcategory, the inclusion has left and right adjoints. So the left adjoint, what it's doing is it's saying, well, I want to make sure everything is concrete. So what I'm going to do is I'm going to blow up my relation to ensure that the diagonal is always in there. So it's just taking a union. And on the other side, we can do is say, well, I want to make sure everything's concrete. So I'm just going to throw away all the elements that aren't concrete. So I'm just going to restrict to a subset and then restrict my relation to that particular subset. Because this is now a reflective and co-reflective subcategory, I should say K only changed the relation where H is changing the carrier. So H is making it smaller, which is it's cutting things down, which is what we want. So yeah, this is now a reflective and co-reflective subcategory. I can move this monad across to here by composing round like this. And so by some general theorems, this category inherits products from this category. So products stay the same, which is what we want. It inherits a monad from this one, which is essentially the monad on this one cut down by the hull functor, and it's Cartesian closed. But the Cartesian closed structure is not preserved by this inclusion. Instead, to look at the exponential in here, I look at the exponential in this bigger place and then cut it down with the hull functor. So the kind of summary for this construction on the category, on this concrete subcategory, is that I can start from a model, a Cartesian functor, a lifting, then I get a CCC, it has a strong monad, and the exponentials in this new category, the exponentials in my category of cryptic relations, cut down with the hull functor. And this is going to be crucial in what comes. So this is how this is the kind of construction, this picture is the construction we're going to use to ensure concreteness. Okay, so the final thing we need to do is ensure that every map preserves preserves the definability relation. And now you might be getting a bit suspicious because there's a kind of circularity here, right? Because I want to build a model in which all the maps are definable. And the way I'm doing that is I want to build a model in which all the maps preserve the definability relation over that model. But then to construct this model, I need to know what the definability relation is over that model, for which I need to know what the model is, right? So I've got this kind of chicken and egg problem that I don't really know where to start. So the kind of trick that O'Hearn and Ricci use is to cut this loop, okay? So if I can say, well, the definability relation is a relation over the model we're interested in, but it's also a relation over our starting model, right? And then instead of having to preserve just def, what I'm going to ask is that it preserves all sorts of relations over our starting model. If, for example, you could say it preserves all the relations over the starting model, then one of those relations would be the definability relation. And so what I get is a model in which all the maps preserve the definability relation in particular, because they're preserving all the relations. So this is how you kind of cut the loop, where you want to say, you use some kind of big quantification, and then we're going to find the definability relation within that big quantification. So let's sort of see how this works. So how do I want to say I can preserve many relations at once. I want to take maps preserving lots of different relations over my original category. So what I'm going to do that is I'm going to say, I'm going to take some indexing set, which is something we're going to work out a bit later, exactly what we want this indexing set to be. And then we can say for every I in this indexing set, if I can pick some Cartesian functor, right, then I can get this picture that we've seen before for every I in I, okay? So this is exactly the picture we've seen before. It's this category of cryptic relations as we've constructed it before. And then what I want to do is I want to not just preserve these relations that I've got in this particular category of cryptic relations, I want to preserve all of them simultaneously over every I. So that what I'm going to do is I'm going to put a big pi here, a big pi here, and then I'm going to take this to be the tupling over all i's of this of these functors, and you get this picture, okay? And then what is an object of this category L? Well, it consists of a carrier A, which is a set, and then this relation A over bar, which is indexed by I. So for every I in our indexing set, the pair A and the relation at I is in the crypt key, is a crypt key relation. So what that means is for every I and every gamma, I'm choosing a family of maps from F phi I gamma into A. So it's for every I and every gamma, I'm choosing a relation over A, okay? So this is how I'm going to sort of talk about preserving many relations at once. If I can, because the maps in this category are maps that preserve every single relation for every single I. And sort of this is very, very loose, but if I choose I big enough, if I choose I carefully enough, then I can set things up so that maps in this category are also going to preserve maps in the eventual category that I'm going to construct. So this is a little bit cryptic now, but I'm hoping that it will come clear as we go along. Okay, so this is how we're going to ensure every map preserves all sorts of relations and hopefully then the definability relation in particular. So now what we need to do is we need to put all these elements together. So this is where we're going to bring all these various moving bits in, and we're going to use them just to build our category, which we're going to call O. Okay, so this is the picture we've already seen. We're starting with any model over, over set kappa. I is still something to be determined. We haven't got there yet. And this is our category L. And what we're going to do is we're going to restrict to the concrete subcategory of L. And it turns out what that means is that it's enough to ask each of these things, rather than being in the Kripke relations, to be concrete Kripke relations. So what that means is an object of this O'Hearn-Ricci model is an object, a pair consisting of a carrier, and for every I, a relation such that the A and the AI together are in the set of concrete Kripke relations over F of phi I. Okay, so this is what our O'Hearn-Ricci model is going to look like once we've picked I carefully enough. Okay, so the question now is, how can we choose I, right? In particular, what we're going to do, we're going to do it like you do when you're doing an induction and you don't really know how strong you need your induction hypothesis to be. We're just going to go along merrily on our way and just keep track of the various things we need, and then just make sure that they're all in the set at the end, okay? And what we're going to need is going to have three parts. So the first thing is we're going to need to ensure that the definability relation is one of these relations here. For some I, we want to make sure that A over bar I is the definability relation, so that then when we preserve all the relations, we preserve in particular definability. The second thing we need to do is we need to make sure that we have a lifting of this monad to up here, so that then we can get a monad on the O'Hearn-Ricci model. And the final thing we need to do is handle base types. This comes back to Neil's question. So we're going to need to do something which is going to give us an interpretation in this model. And these are the three things we're going to need. So we're going to take them in turn. So starting from this first one, I've just put in the corner a little reminder of what it means to be an object in the category O. So what we're looking for is we want to say, we want some interpretation of types in this category O and some I in the index set, so that the relation at I and context gamma at the interpretation is exactly the definability relation over O. Now, this doesn't quite match because the definability relation over O is a subset of maps over O, whereas up here we have maps in set K from F phi of gamma into the carrier. But not to fear, because if we take the forgetful functor which just throws away the relations and just looks at the carrier, then this Hom set is a subset of this Hom set. And so what we're going to ask for is that this functor U, D, that does first the interpretation D, and then the forgetful functor is going to be somewhere in our relation, it's going to be one of the F phi I's. Because then if we feed in U following the interpreted at gamma, we get exactly this. And so we can match this with the definition of O, so that then this has a possibility of at least being well typed. So that's our first thing. We're going to first take all Cartesian functors into our model. This is one of the reasons why we're taking a small subcategory. There might be neater ways to get around this, but this does the job. Okay, that's the first part done. The second part is we need to pick a monad lifting. So we've got our monad down here. We want to lift it to a monad up here so that we can get this new composite monad over here. And it turns out that the way to do that, it's good enough to define a lifting for each I in I. And so what we want to do is we want to make sure that we have a lifting parameter for each I and for each phi I even. We want to make sure that we can choose a lifting parameter such that for each of these categories, we can lift the monad to some monad Ti in it. And then sort of these pointwise determine this monad here. Actually, what we go on to do for the proof later on, we want to be able to choose these lifting parameters very carefully. In fact, we're going to want to choose them based on the definability relation as well. So what we're going to do is we're going to take for each functor f, we're going to take a collection of parameters for top-top lifting, and we're going to take all of them, all the parameters for top-top lifting. I haven't gone into detail of what these really are, but these do form a small set as well. Okay, the final thing we need to do is we need to work out our interpretation of base types in our category O. Okay, so we want a mapping which goes from the base types into our category O, and we want it to lie over our original interpretation S. So what does that mean? It means that the interpretation of base type beta needs to have carrier the interpretation of the base type beta in the original model, and then it needs some extra relations which we need to work out. What do these things need to look like? Well, the definition tells us that for every I in I, we need to show that we need to give something such that a relation that this is in the concrete Kripke relations for f of phi I. Okay, so what we're going to do is we're going to once again quantify over everything, because we want to pick this carefully at the end as well. So we're going to quantify over all maps such that S of beta, R of beta lies in the concrete Kripke relations over f of phi I. Because then what we're going to want to do is at the end, for our interpretation of base types, we're going to have maybe some extra junk here, well, not junk, extra parameters here we're not currently interested in, and then at the functor f of phi I and the mapping R, we can just do what R tells us to do, which means that then this holds, which is exactly the condition we need for our interpretation of base types to be well typed. So O'Hearn and Ricci don't have to do anything like this, but this is what we're doing to handle base types. Okay, so if we put this all together, this is our...
Sorry, one more question here.
Yeah, go on.
So you said O'Hearn and Ricci did not need to do this. Yeah. And you also said they did not have base types in their model. Would they have had to do something like this if they wanted base types?
I think so, because you need to, because you don't know, let me think of the best way to say it. Yes, because you at some point you want to do some inductive argument, and if you're working without base types, you can just start from the terminal object, which is already determined. But we want to do some inductive argument starting from base types based on a very particular choice of R. If we didn't have any base types, we don't need to pick R, because we know it's going to be right in the terminal case. But once you add in base types, then you need to somehow handle that. So yeah, that's the extra kind of the thing you need. Yeah, so this is the three components we now have. One thing to handle to make sure that the definability relation has a chance of being one of the things that the relations that's being tracked in our category O. One thing to make sure we have a monad lifting, and one thing to make sure that we have an interpretation of base types in O. And then what we're going to do is we're going to stick all these together into one big fat set. But I'm reasonably sure that it still remains small, which is good. And then to say, well, what functor do I need to pick for this f, k, and r? I can just take the functor f. And now this is the nice thing. So when the interpretation of base types, the relation at a base type beta for f, k, and r is just going to be r of beta. And by this, this will be well typed. Okay, so let's see what we've got. So now we have this big collection of parameters, okay? And now what does it mean to be the interpretation of a type d sigma in this category at the relation at f, k, and r and a context gamma, instantiating this with I being f, k, and r? What that means is it's a collection of maps from f of gamma into the carrier of d sigma. Okay. In particular, if I take the Cartesian functor, which first does the interpretation in O and then throws away all the relation, just looks at the carrier, then that is a subset of this Hom set. Okay. And like we said before, the definability relation on O is a subset of the same Hom set. Okay. So at least we have a chance for these two being equal if we can pick K and R correctly. So then the key property of this model, of the O'Hearn-Ricci model, is the fundamental lemma in some sense, but you can't call it a fundamental lemma because that name's already taken, is that for some choice of f, k, and r, there is the interpretation of sigma, the relation on the interpretation of sigma is exactly the definability relation. And then if I have a map between the interpretation of gamma to the interpretation of sigma, it's going to have to preserve all the relations for every f, k, and r. In particular, then it'll have to preserve the definability relation. In particular, then it will be definable. So this is the kind of the property that makes sure that the O'Hearn-Ricci model is fully abstract. So this is the summary of where we've got. So this is what objects of O look like now. This is our interpretation of base types. And now we need to think, well, how can I sort of make this happen? So how can I pick f, k, and r so that this will work? So remembering once again, we have this nice chain of inclusions. So then if I take the functor to be the composite of the underlying functor following the interpretation in our category, k to be something that I'm not going to tell you, but you have to pick it carefully, and r to be the thing which just says at beta, giving back definability at beta, then by the definition of this thing here, that means that our induction can get started because the relation at these three parameters is exactly the definability relation over O. So this is why we have to quantify over all possible R's, because until we've constructed O, we don't know what this is going to look like. So we can't write down this until we've constructed O. But once we've constructed O, we can find this as one of the things we've already quantified over. And likewise for this relation, actually, and likewise for this parameter. So we can rephrase our key property a little bit more precisely now as saying this, that if our interpretation of base types is concrete, if in an appropriate sense, then for every type sigma, at these three parameters, the relation that we're getting is exactly the definability relation over O at sigma. The proof here is an induction. And in case you're thinking that I've forgotten exponentials and matic types or concreteness completely, concreteness is actually needed for this induction here. It's a kind of crucial part of this induction. But now we can go from this key property to full completeness of this model, because if I have some map from the interpretation of gamma to the interpretation of sigma, then this map is going to preserve every relation. So if I've got H in FKR, the relation at FK and R and context gamma, then F of H is at the relation at FKR and context gamma. In particular, picking these three parameters, it means that if H is definable, then F following H is definable. And so in particular, because the identity is definable, F is also definable. So what this means is you get this theorem that says that if we have this concreteness result of our base types, then this model is fully complete. This category is extensional because it's overset, which is itself extensional. Therefore, this model is fully abstract. The final, I just want to say, there's a little kind of comment here. I think this is not, this looks like a sort of strange and quite strong property, but I think it's actually not that strong, and you can get it from full completeness at base types of your original model. I think I need to go and check that. Okay, so let's sort of sum up everything that we've seen. So the kind of high level picture is this. So full completeness and extensionality implies full abstraction. I think there's more subtle things you can do with instead of extensionality, but for now this is good enough. Definability is a logical relation. And moreover, if a map preserves definability, then it says is itself definable. So we have this, you can characterize definability for your language. And maps in the O'Hearn-Ricci model preserve enough relations. They preserve so many relations that in particular, they preserve definability over the O'Hearn-Ricci model, and so they become definable. And this extends to the computational lambda calculus over a general model with some assumptions, but some of this is in the sort of still to do column. In particular, weakening this extensionality assumption, working out exactly what assumptions we need to get the hull functor H. At the moment, the assumptions I feel are quite strong, but I think we can do something a little bit weaker to make sure that it exists in the general case. Because the examples that we'd really like to get to especially include pre-sheaf models like names or quasi-Borel spaces. And so then we really want to get away without this kind of extensionality assumption. And finally, that we want to enrich the language more with effect operations or primitives or something like that, and also with sum types where sort of these two bits, I think, I know are fine for some types, but exactly how the O'Hearn-Wiki model would work, we need to sort of work that out. But that's everything. So if you've got any questions or comments, I'd be very happy to have them.
Okay, so I guess let's first thank Philip for the talk, for the great talk he's given so far. If you'd like to unmute yourselves and that'd be great. Yeah, I guess, are there any questions?
So I think the obvious one is what happens if you've got recursion. I mean, if you're really going to do this for PCF.
If you do this for PCF, at the moment, I don't know. If you're going to have to enrich it all, I think. And if you look at the O'Hearn-Wiki paper, that's essentially what they're doing. The O'Hearn-Wiki paper implies that it would work okay, but I haven't sat down to think about it at all yet. So I think order enrichment should be okay. But whether everything works once you get into the nitty-gritty, I still don't know.
I have a small question that might be pretty simple to answer here.
Mm-hmm.
So in one of the first slides, you defined both full abstraction and adequacy.
Mm-hmm.
Is this model, do we know for this model if adequacy also holds?
I believe, I haven't thought about it in great detail actually. Adequacy is usually, I haven't thought about it, so I don't want to give a conclusive answer, but I think it will be without too much difficulty, assuming your original model is adequate. I think this model should be, but I need to think about that. That's a good point.
I have a question about these concrete objects and the subcategory of them.
Yeah, yeah.
Is there some universal property of the subcategory of concrete objects with respect to the crypt key relation category? Is it some sort of completion or co-completion in some sense?
Well, it's reflective and co-reflective subcategory, which is, I guess it means it's the category of algebras for an idempotent monad or something like that, right? There's some theorem along these lines. If it's a co-completion or complete, I'm not sure. I don't feel like it is, but I wouldn't bet too heavily on it. Yeah, so it may be, but I think beyond asking for, asking for those two adjoints to exist, I don't know what other sort of special properties it might have.
Also an observation, which was this boldface F you defined. It looks very much like a sifted co-completion, or the definition of local strong presentability. But you need to replace set K with, or set kappa with set. So I'm not sure if that's related at all, but it's reminiscent, I thought, of presentability. And so that also links with size issues. So. Is
that in the definition of I? This one?
Yeah.
Yes. Because the thing is, if you did it over an arbitrary model C, this would just be Cartesian functors into C, where then you need C to be small so that this set remains small. So. Like set doesn't really, the fact that we're doing it over set kappa here is kind of just an accident of the presentation rather than a fundamental thing, I think.
Right, okay.
Are there any more questions? If not, I guess I'll pause the recording here and